In this video, I will introduce the idea of Taylor and Maclaurin series. And before we begin, let's recall that we know what series are and what power series are. So for example, if we have a power series that is centered at some value C, we know that this power series on some interval of convergence may act like a function, and we may or may not know what that function is. However, we do know some examples of knowing what a power series representation of some function would be on some interval of convergence, such as this one. The question that we have is a more general question, that is, so the question that we're trying to answer is whether for a function such as e to the x, whether there exists a series that acts like that function for some values of x around c. This is what we want to be able to answer, and we can be a little bit more specific before we start centering the series around some value c. We can center it around 0, for example, and then the question would look something like this. If such power series existed, would we know what it is? Is there a way to find out what that what that series is? And if we are interested in finding this series, what does it mean to find such series? Well, to find series means to find the coefficients. So if we know what those coefficients are, and basically they are the only things that determine what the series should be, and for example, in the example above, all such coefficients are equal to 1, and this is how we know the series for this given function. So to find the series means to find the coefficients, and if we want to find a power series representation of some function, we should focus on finding the coefficients of that power series. So this is just an idea. So if we actually, so let's just write this out. So the idea is, if we want to find the power series, and let's just focus on the power series centered at 0. So if we want to find the power series for this given function, we want to find these coefficients. This is the problem that we have, and we're going to try to address next. And let's write out a few terms of this series and see if we can find the relation between the coefficients and the function somehow. And we're considering all of this near 0. And the first relation can be observed by replacing x with 0 and realizing that when you plug in 0 into the series, this whole thing will be equal to 0. So that means we now have a formula for finding the 0th coefficient. It will simply be equal to the value of the function at 0. Alright, so one down, infinitely many to go, because remember, we need to find all such coefficients, and there are infinitely many of them. To find the next one, let's differentiate the function. So we're going to differentiate this function, and as we do that term by term, the 0th coefficient is gone because derivative of a constant is 0, but derivative of a1x is just a1. Derivative of a2x squared is going to be 2a2x. So we just differentiate using the rules of differentiation. It is possible to see the pattern there, but most importantly, when we plug in 0 for x, we'll have all of this turning into 0, and the only thing that's left is a1, meaning we found a formula for a1. It's just going to be the derivative of the function evaluated at 0. So in the same manner, we can find the second derivative. It will be 2a2 plus 3 times 2a3x plus 4 times 3a4x squared plus, and so on. And then plugging in 0 for x, we'll get rid of all of this, and we'll only have 2a2 left, and then a2 therefore will be equal to the second derivative at 0 divided by 2. And now we are ready to actually try to figure out the pattern, right? So the third derivative we're gonna write out with the goal of figuring out the pattern. So when we plug in 0 into the third derivative, we're going to have 3 times 2, which is 6a3. So a3 will be equal to the third derivative evaluated at 0 divided by 6, but that 6 can be written as 3 times 2. So what is the pattern here? To actually identify the pattern, let's see what happens when we take the nth derivative. So taking the nth derivative will effectively eliminate the first n terms of the series, and we're going to end up with the nth coefficient, but the x here will have power 0, so I'm not going to be writing it. And the question is, what will be the coefficient in front of an? Every time we take the derivative, that coefficient comes down, so it's n times n minus 1 times n minus 2, and so on. And for that we have a special notation, n factorial. And the n plus 1th term will become, again, there's no need to write out all these coefficients here, because when we plug in 0 into the nth derivative, all of this will turn into 0. So the nth derivative evaluated at 0 is equal to the n factorial times a sub n, meaning a sub n is equal to the nth derivative evaluated at 0 divided by n factorial. And by the way, in order for us to be able to find the nth derivative, we have to assume that this function So this must be an assumption. And if this assumption is not satisfied, then it's not going to work. F of x has all derivatives. So this is an important assumption. If f of x doesn't have any of the derivatives, then we simply won't be able to find that derivative. But if it does, so here's what's going to happen. The nth coefficient can be identified with this formula. So the conclusion that we're going to draw from this is that we had a function and we were able to produce this power series, and this is true. We wanted this to be true. However, we have an issue here that we don't know for which values of x this is true. So all we know at this point is that this is true for some values of x, and this set of values of x may not be the same as the interval of convergence of this series. So we definitely know it has to be true for some values of x. It's just that interval can be less than the interval of convergence of this series. So this is a conversation that we're going to avoid having right now, and we will have it later on, because there are examples of series out there which converge on their intervals of convergence to a function that is different from the function from which they were obtained. So again, here we're not going to be concerned with the interval of convergence for a moment, but what we have created has a name. So this particular series was created using this particular formula, and the series created from some original function f of x using this particular way is called Maclaurin. Maclaurin series. So again, what I want to mention here, and try to avoid having this conversation until we are ready, is that the interval of convergence of this series, so we haven't discussed this, the interval of convergence of this series may not be the same as the interval on which this series is equal to f of x. So ideally they should be the same, but they may not be. And this is the reason why we're not going to talk about the interval of convergence here, and we're going to take some of the facts for granted. Now, with this in mind, let's find the Maclaurin series for the natural exponential function. So to find the Maclaurin series, we're going to use this formula. When you use it a few times, you'll be able to remember it. In this formula, n is just some arbitrary natural number, and we have to find nth derivative and evaluate it at 0 and divide it by n factorial. So the first thing we're going to do is we're going to start with n equals 0. So when n equals 0, we're looking at the function itself, and we evaluate it at 0, and we find the 0th coefficient by taking that and dividing by n factorial. 0 factorial is 1, so the whole thing is equal to 1. Similarly, we find the first derivative for the natural exponential function. These computations are rather too straightforward. It's straightforward to the point that we can generalize. So the nth derivative is e to the x. At 0 it's equal to 1, and the nth coefficient will be equal to 1 over n factorial, meaning that we can now write e to the x as the following series. Which in general can be expressed like this. Now, let's find out what the interval of convergence of this power series is. So it can be like a whole separate problem. And to do this, we're going to use our knowledge of power series from one of the previous lessons. So we're going to set it up as a limit. As n goes to infinity, we're going to take the n plus 1th term and divide it by the nth term and take the absolute value. And here's what we get. So the whole thing is equal to 0, which means that the interval of convergence is from negative infinity to infinity, with the center of convergence at 0 and the radius being infinity. However, this alone doesn't guarantee that. So again, if we would imagine this is our interval of convergence to be, it doesn't tell us that on its entire interval it converges to e to the x. So this is something, so this full equality we shouldn't be taking for granted right here. It will require an extra step to convince us, but we're not going to make this step right now. So for right now, again, we're just going to assume that this is true for some values of x, not necessarily on the entire interval of convergence. All right, excellent. So let's do one more problem like this. Let's go ahead and find the Maclaurin series. For the sine function. And we're going to do the same thing. We're going to use the formula that we derived earlier. And we're going to start with n equals 0. We're going to evaluate it at 0. It's 0. So the 0th coefficient is 0 over 0 factorial. It's 0. Now the first derivative of sine is cosine. So the first derivative at 0 is 1. So the first coefficient will be 1 over 1 factorial, which is 1. The second derivative is negative sine x. So the second derivative at 0, it's again 0. So the second coefficient is 0 over 2 factorial, which is 0. Continue with the third derivative, it will be negative cosine x. So third derivative evaluated at 0 is negative 1, meaning the third coefficient will be negative 1 over 3 factorial, which is negative 1, 6, and so on. And luckily, the derivative of sine, it's either cosine, the derivative of sine is cosine, but if we continue taking derivatives, we're going to observe this pattern, sine, cosine, negative cosine, and it's going to go back to sine. Therefore, we can try to predict we're only interested also in odd derivatives, so all the even derivatives will be equal to 0 at 0, so we don't really care about those, but for some odd derivatives, it's just going to bounce between plus or minus cosine of x, so we can express it like this. And that means the derivative, when you evaluate it at 0, will simply be negative 1 to the power k, and that means we can find every odd coefficient using this formula. Meaning that sine of x is equal to, or can be expressed as x minus 1 over 3 factorial x cubed plus 1 over 5 factorial x to the 5th minus 1 over 7 factorial x to the 7th, and so on. Or in general, it can be expressed as k goes from 1 to infinity, and it's going to be negative 1 to the k over 2k plus 1 factorial x to the power 2k plus 1. And again, we know that the interval of convergence of this series may not be exactly where that series converges to the function sine of x. So eventually it will work out nicely, but for right now, I know we haven't proved it yet, so it's just a wishful thinking here. Now that we know the power series, which is called Maclaurin series representation of sine of x, we can just like that. So if sine of x is equal to x minus 1 over 3 factorial x cubed plus 1 over 5 factorial x to the 5th minus 1 over 7 factorial x to the 7th, and so on. So if this is the formula, so this is the power series representation of sine of x. We can use the same way, or we can use some properties that we learned earlier. That is, we can differentiate the sine of x term by term to obtain the power series for cosine. And the power series for cosine will probably look something like this. We're going to have -1 to the power k over 2k factorial, and here I should have done this. There you go. And we can do this to come up with Maclaurin series for any other function that has infinitely many derivatives. So one result of such work can be this table that summarizes the Maclaurin series for some of the basic functions. And remember, everything that we've done here was with us being interested at some function at 0. So if we go back over here, remember we were exploring what would come out of this relation if we're interested at 0. However, we're not always interested at looking at function only at 0. So the next question that we want to try to answer is what if we change the center of the series and move it to some arbitrary value c, and in other words, what if we assume that we have a nice function? Nice means has all the derivatives, so all derivatives exist, and well, can we find these coefficients then? So this is an equivalent of us looking at a function near some point C, which we would refer to as the center of the series. And we're going to do the same process as before, so I'm not going to be writing all the details, but just like before, we can write out our function, but this time it will be centered at C. And we're going to find the coefficients a sub n by discovering the relations between the coefficients and the function itself. And if before we were evaluating the function at 0, now it seems like it makes sense to evaluate it at c, because all of this will be equal to 0, and the only thing that we have left is the 0th coefficient, and there you go. The 0th coefficient is simply equal to f of c. Very similarly to the previous process, we're going to differentiate the function. We're going to see how things work out when we differentiate the function, so that when we evaluate the derivative at c, we are now going to lose all of this, and therefore a1 is equal to the derivative of the function evaluated at c, and so on and so on. So it's not going to be too hard to notice that the formula for the nth coefficient would be the derivative, the nth derivative of the function evaluated at c divided by n factorial. And once we notice that pattern, once we notice this pattern, we'll be able to construct the power series using these coefficients. And just like before, this power series, well, we want it to be equal to f of x. However, the interval on which it is equal to f of x may not be necessarily the same as the interval of convergence. We haven't established that relationship yet. But assuming that everything works out nicely, this power series is equal to f of x, and this particular power series is called the Taylor series of f of x at x equals c. So it's not too hard to notice that the Maclaurin series, or what we call Maclaurin series, is actually the same as the Taylor series. So meaning every Maclaurin series is the Taylor series, but not every Taylor series is a Maclaurin series. So Maclaurin series is the Taylor series centered at 0. However, if you move the center away from 0 to some value c, then such series is now called Taylor series. So let's do an exercise of finding the Taylor series. And let's do the same function, but let's move it to the right 1 unit. And we're gonna do the formula just like before. So the process of finding Maclaurin and Taylor series is very similar. Not similar, it's the same. We're gonna find the nth derivative, evaluate it at c, and then divide it by n factorial. So we're going to start with n equals 0, and we're going to evaluate it at 1, and we're going to plug it in. And we're going to continue this process. And we're going to continue again, and e to the x is such a nice function that we'll be able to exploit the pattern very soon. And the nth derivative is e to the x, so the nth derivative evaluated at 1 is always going to be e, so the nth coefficient will be e divided by n factorial, which means that we are now ready to write the Taylor series for e to the x. It's going to be e plus e times x minus 1 plus half of e x minus 1 squared plus e over 6 x minus 1 cube, and so on. And in general, this can be written as e over n factorial x minus 1 to the power n goes from 0 to infinity. And that's what we call the Taylor series for the natural exponential function centered at 1. We can find the interval of convergence for this series by setting up the limit as n goes to infinity of the n plus 1th term. But as you can see, things work out exactly the same way as with the Maclaurin series. and we're going to have limit of 1 over n plus 1, which is 0. So that means while this series is centered at 1, the radius of convergence is infinity, so the interval of convergence is from negative infinity to infinity. And once again, we don't know that it converges to e to the x on this entire interval yet. We haven't proven that yet, but at the end of the day, it's all gonna work out nice for nice functions. Let's find another Taylor series for a function arctan x, and let's do that also around x equals 1. We're gonna be using this formula again. So first step is for n equals 0. So we have f of x when n equals 1. When n equals 2. And I'm gonna push it here and try to find it for n equals 3. Derivative of the numerator times the denominator minus derivative of the denominator times the numerator. So we're going to put plus 2x here. 2 times 1 plus x squared times 2x divided by 1 plus x squared to the power 4, and the third derivative at 1. We're going to have the denominator is 16 and the numerator is, we have negative 8 plus we have 1, 2, 3, 4, 5 times 30 times 2. We have again 8 times 8, like 64 or something. So we have 56 over 16, which is 7 halves. So the third coefficient will be 7 halves divided by 3 factorial, so 7 twelfths. And what we've learned from this is that arctan of x can be expressed as pi over 4 plus 1 half times x minus 1 minus 1 half x minus 1 squared plus 7 twelfths x minus 1 cube, and so on. So I'm not going to try to find the actual formula here, but this is a power series representation of arctan x around x equals 1. We can always check our work with Wolfram alpha. So for example, in this case, all you have to do just type Taylor series of arctan x at x equals 1, and Wolfram alpha is definitely better at computing this type of stuff. So it looks like we got the first 1, 2, 1, 2, and that's it, coefficients, right? That means I made a mistake somewhere here, so I do see one mistake. This should have been 64. This should have been 16. And then this will be 112. I do see that. I don't see... This would be... Oh yes, we have... I forgot another 2 over here. That's right, because we have to divide by 2 factorial, right? So we have negative 1/2 over 2 factorial, which gives us negative 1/4. So this is negative 1/4. So we did find the Taylor series of arctan around x equals 1. Now that we know how to find the Maclaurin and Taylor series for basic functions, we can combine this skill with the one of being able to integrate and differentiate power series to create new power series, and we can use all those skills to find the Maclaurin series of a function, something like this. For example, here's what we're going to do. One way we can do it is manually by setting up this formula and differentiating and all that stuff. However, we can do it by obtaining this Maclaurin series for cosine, and that being our starting point means we can actually, to find the Maclaurin series of this original function in question, we can do it in steps. So we can first find the Maclaurin series of cosine x squared by replacing x with x squared in the formula, etc. So the general formula would look something like this. So instead of x, I'm going to put x squared in here. And then we're just going to throw an extra x in there. So actually, I don't even need this whole middle part, right? So we can just work with this as an identity, as we have done before with other functions in their power series. So now to multiply this by x, we just have to multiply this by x, but multiplying this by x means we just can carry it over inside, and bringing it over inside just means we just throw another x right over here. So the final answer will be the Maclaurin series for this function would be negative 1 to the power n, x to the power 4n plus 1 divided by 2n factorial. So we found the Maclaurin series of some function that is absolutely not trivial, and we did it. What we learned right now is we've been introduced to the idea of Taylor and Maclaurin series, and we learned how to find Taylor and Maclaurin series for any given function that has all of its derivatives. What we didn't do is we didn't convince ourselves that the series that we obtained is the series, or rather that the series that we obtained converges to the original function from which it was obtained on its full interval of convergence. So we haven't done that yet. That's still to come.